We are actually discussing oxidation numbers in stoichiometry. Actually, we started the topic stoichiometry. In this, we are supposed to know few things. Let me actually get you through a ride of what exactly we are doing in stoichiometry. You must understand that first. So let us take a ride on what we are doing. Observe carefully here. In this chapter, what you must know is basically the concept of mole, right? And second, your applications of mole's concept, application of mole concept. Now, what do you mean by application of mole concept is, right, you must understand that you can have problems in this. Number one is a weight-weight relationship. You must understand this. The problems might include a weight-weight relationship, meaning you are actually having to find out the LHS, you're given some weight and you're supposed to calculate the RHS, that is the product's weight. Such a relationship in a balanced equation between weight and weight can be called as what? A weight-weight relationship issues, right, or problems, right? And you can have even weight-volume relationships, right? So you can have problems where they're broadly classified. You know, if you are good at concept, you don't require any classification. You don't require any classification if you're good at concept, right? Straight away you can do the problem. So what is a mole concept? You must understand, because that is the basic language in chemistry. So whenever you go through a balanced equation, a stoichiometric equation. Now, what's a good stoichiometric equation? Sometimes people call it to be a very good stoichiometric equation. Now, what is a very good stoichiometric equation is, it must be balanced. Second thing, what it should show you is basically the states in which the reactants and products are there during the formation and during the initial states. So the reactants and products are shown their states. First, it should be balanced, then the states of the reactants and products. And the third thing, when the reaction is proceeding from LHS to RHS, heat is absorbed or evolved. Even that is actually shown in the equation itself. Then these three things, if they are fulfilled, then we say that the equation is a stoichiometric equation. You must understand. Now, once you have a stoichiometric equation, then the language what we use is the mole language in chemistry, right? When you do that, then broadly I can classify the issues or the problems into weight-weight relationship issues, weight-volume relationship issues, and three even volume-volume relationship issues. Volume-volume relationship issues, and even sometimes we use the limiting reagent problems. Right, and even I can simply say the fifth one is the concept-based. The concept-based problem. So broadly, once you know what is a mole concept, and once you have before you a stoichiometric equation is a well-balanced equation with showing the states in which the reactants and products are there, and even the heats evolved or absorbed, then such an equation can be called as a stoichiometric equation. Once you have that, then I think there are several issues propping up that is broadly classified into 5 issues. That's number one is weight-volume, limiting reagent, concept-based issues. And these are the 5 broad ways I can actually classify the entire problems that involves what? A mole relationship. You must understand that. Other than that, then you have 3. You must know what are concentration terms. Concentration terms, which might include molarity, which might include normality, which can be percentages, W by W, or percentages W by V, right? You have all these concentration terms to express the concentration of solutions which are labeled outside in the laboratory, right? That's one. And 4, we would like to introduce the concept of oxidation number, right? Then we get into what are redox reactions and what are disproportionation reactions. Then you have your molecular formula and empirical formula, and you have a relationship between these two and the host of other issues. This is what we are actually running through the entire stoichiometric chapter. So once you are starting a chapter, you must be knowing in advance what is that you are running through. So if I take you through a ride of it, first of all, you should know what is what? A mole. Then applications of the mole concept, what I call it to be a chemical language which we are supposed to use it when you have a stoichiometric equation before you. Broadly, that can be classified as weight-weight relationship, weight-volume relationship, volume-volume relationship, limiting reagent issues, and concept-based issues. Right? We will deal with each one of them. And the other one is, of course, the concentration terms, the formulae involved, molality, normality, percentages, oxidation number, redox, disproportionation, molecular formula, empirical formula, and a relationship between them. Right? Let us take one by one all these even the problems, and let us even discuss redox, disproportionation, and all these issues. Right? Let's take one by one. Watch carefully here. Please watch. Please watch here. Now, as I have written, what is a redox reaction? What is a disproportionation reaction? Let us actually start from there. This I call it to be an application of oxidation number. And let me tell you what is a redox reaction. Right? What is a redox reaction? Now, what is a redox reaction if we wanted to know, right? First of all, we should know what is oxidation reaction, what is reduction reaction. Let me tell you, this is what it is. When there is increase in oxidation number, remember that. When there is an increase in oxidation number of an element in a compound, in a reaction, then we say this is what increase in oxidation number, this is what we call it to be oxidation. And reduction or decrease, what I call decrease in oxidation number, which we call it to be reduction. So using oxidation numbers, we can actually judge whether the reaction, whether an element is getting oxidized or not in a particular reaction, or an element is reduced or not in a particular reaction. You must understand, right? Once you know what is a reduction reaction, what is an oxidation reaction, then redox reaction is simple. And I would like to define what is a redox reaction. Observe carefully here. A reaction in which both oxidation, reduction takes place. Oxidation and what? Reduction both take place. Then reduction and oxidation both take place. Oxidation and reduction both takes place, and this is what is called a redox reaction. You must understand. Right? A reaction in which both oxidation and reduction will be taking place can be called as what? A redox reaction. You must understand all the reactions that happen, that happen in cells, right? In cells are all redox reactions. You must understand, right? For example, if you actually see one of the reactions which I'm about to write it, examples. If you look into the examples, watch carefully here. Here is a manganate ion, and it is treated with Fe plus 2. Then it got reduced to Mn plus 2 and Fe plus 3. Right? This is what it is. An ionic reaction. This represents ions, so this is an ionic reaction. Now we have to check whether it's a redox reaction or not. If you wanted to check it, then a reaction in which both oxidation and reduction takes place is nothing but redox. So what you do is you just calculate the oxidation number of manganese here. So it's basically X. Minus 2 into 4 is minus 8. Minus 1. So the oxidation number of manganese here is plus 7. Right? And now what's happening to manganese, if you actually see here, it is actually plus 2. So it is 7 to 2 is basically decrease, right? When you have decrease in oxidation number, then it's nothing but reduction. So basically manganese is reduced from plus 7 to what? Plus 2. So reduction has been fixed now. Now coming to the oxidation, you can actually see here plus 2 is getting oxidized to plus 3, right? Plus 2 to actually plus 3. Basically this is oxidation. So in this actually you can see manganese getting reduced, and from Mn plus 7 to actually Mn plus 2. So this is basically reduction, and Fe plus 2 is getting reduced, oxidized to Fe plus 3. This is oxidation. Both are happening in the same reaction, so I call this to be a redox reaction. You must understand here. Right? You must understand here. Right? If this is the case, even I can give you another reaction. Look into this. For example, if you actually see this reaction, right? Copper oxide plus ammonia, then you get Cu plus N2 plus H2O. You watch this reaction. Now what is happening here is the copper is plus 2 here. This is in elemental state, it is 0. And the nitrogen here is minus 3, and it is becoming 0. So you must understand plus 2 to 0 is basically reduction. Minus 3 to 0 is oxidation, so there is increase. Minus 3 to 0 is increase, right? So I can simply say here that copper is reduced and nitrogen is oxidized. So both are happening at the same reaction. So I call this to be a redox reaction. You must understand, right? And it is a redox reaction. Now, you know, the questions which are asked in the JEE, one of the questions says, which of the following is a redox reaction? Which of the following is a redox reaction? That's what being asked, right? And which of the following is a redox reaction? Then we have our definition. Both oxidation and reduction must be taking place. That's called what? A redox reaction. Both oxidation and reduction should be taking place. Right? Then such reactions are said to be what? Redox reactions. And the examples are these, and I can give you a number of reactions. All the reactions that happens in what? Galvanic cells are all redox. One is oxidized, the other is what? Reduced. So these are all oxidation reduction reactions, which are otherwise called what? Redox. Right? You have other category, that's nothing but disproportionation reactions. Now what are disproportionation reactions? Let us understand. Now watch carefully here. What is a disproportionation reaction? Look into this. Please look into this. Watch carefully here. Please watch. Please watch. What is a disproportionation reaction? What is a disproportionation reaction? First of all, understand disproportionation reaction is also a redox. Right? Remember that disproportionation reaction is also a redox reaction. So if someone is asking you what is disproportionation reaction, it is also a redox reaction. It is also a redox reaction, but the only difference is, right, I would like to define what exactly is this. A reaction in which same element, I would like to underline, same. It is the same element. Same element. It is the same element. Same element. Right? Remember, a reaction in which the same element undergoes both oxidation and reduction. Well, whether it is same element or different elements, a reaction is happening where both reduction and oxidation is taking place. So disproportionation, I would like to consider is also to be a redox reaction. But the only difference is the same element is undergoing both oxidation and reduction. Right? And this is what is called a disproportionation reaction. Disproportionation reaction. Now, what is the subject point here? Remember one point here. Someone is asking you, what is the action of halogens on, this is the question, what is the action of halogens on bases like caustic soda, Now what is caustic soda? Sodium hydroxide. If someone is asking this question, what is the action of halogens on caustic soda? If that is a question posed to you, then you must be answering in this fashion. In fact, I would like to write it here. All halogens, right? The question is, what is the action of halogens on bases like caustic soda? This is a very important question in your exam. This is very, very important. So all halogens undergo the disproportionation with NaOH, with bases. And I am now dancing for a movement such as you understand properly. Right? Let me dance. So all halogens undergo disproportionation with NaOH. And I am dancing for you. Here is. Right, I am underlining. That's what I meant by dance. So understand, all halogens undergo disproportionation with NaOH except fluorine. You must understand. And let me also remark something such that it will be easy for you in your lifetime till you die. Remember that fluorine never gives, right, never participates. Remember, never participates in redox. Never participates in what? A redox reaction, you must understand it. Right? It never participates in what? A redox reaction. And what is the action of halogens on bases? If someone is asking, all halogens will be undergoing disproportionation except what? Fluorine. And fluorine will never undergo what? A disproportionation reaction at all. You must understand this. Right? For example, let us take the case of fluorine with NaOH. Fluorine with NaOH. Now what is the reaction about? Fluorine with NaOH. Right? This is what you are supposed to get. NaF and OF2 and water. This is what is the reaction. Fluorine with NaOH. That's what is the reaction. Now, is it a redox? No, absolutely not. Is it a disproportionation? No, it's absolutely not. Look into this. Now, look into this. This is the oxidation number of fluorine is 0. And here it is -1. And in OF2 also it is -1. Look into this. OF2 looks like this. And it is pulling, it's pulling. You develop a double positive charge here. This is negative, that's negative. So 0 becoming -1, 0 becoming what? -1. Fluorine is, oxidation number is actually what? Reduced, right? And fluorine 0 is becoming -1. 0 is becoming -1. You must understand. So where is the question of oxidation and reduction? You must understand. Fluorine oxidation number is decreased from 0 to -1. So fluorine is getting reduced. In both the cases, both the compounds which are formed, it is only getting what? Reduced, and it acts as a very good what? Oxidizing agent, because an oxidizing agent is that where it reduces itself but never gets what? Oxidized. You must understand this, right? So fluorine oxidation on bases is this way, that it has only one oxidation state, 0 to -1 and 0 to -1. This is reduction and this is reduction, and this is, I can call, this is not a redox. And that's a very important question which I'm actually telling it to you. You can bank on while writing your pre-engineering tests or pre-medical tests. So what is the question here? What is the question here? What is the action of halogens on bases? Well, I would like to underline that all halogens, you take any halogen, all halogens, and I'm dancing here, will undergo disproportionation, and I'm telling you except what? Except what? Fluorine, you must understand. Fluorine, in fact, never participates in a redox reaction because it's always reduced, oxidizing the other guys. You must understand this, right? So no disproportionation reaction for what? Fluorine, you must understand. Then what are the other reactions with the halogens? Observe carefully here. If this is the case, Then what is the action of chlorine, bromine, and iodine? What is the action of fluorine, bromine, and iodine? Let us see this. Watch carefully here. As I said, chlorine, bromine, and iodine plus NaOH shall undergo disproportionation. Disproportionation, you must understand, disproportionation. Now, what is disproportionation? A reaction in which the same element will undergo both oxidation as well as what? Reduction is called a disproportionation reaction. Now, look into this. Right, this chlorine, it is cold, dilute, NaOH. When you treat this, then you're supposed to get ClO, Cl minus, and ClO minus. Look at this. If it is cold, dilute, NaOH. Similarly, if it is hot, right, hot and concentrated, then you will get Cl minus and ClO3 minus. You must understand. ClO3 minus. And when we wanted to calculate the oxidation numbers, 0 is becoming minus 1. 0 to minus 1. 0 to minus 1 means it is reduction. It is reduced. Right? And the same 0 is again giving you x minus 2 is minus 1. So x equal to plus 1. So it is basically, if you say this, there's the same 0 is giving you plus 1. So this is oxidation. And if you actually see, it is the same chlorine which undergoes both oxidation and reduction. Same chlorine is oxidized as well as reduced. So it is 0 to minus 1 and plus 1. This minus 1 is the Cl minus and this plus 1 is ClO minus. Since the same element is undergoing both of this is called disproportionation. Disproportionation, you must understand, disproportionation reactions. Similar would be the reactions of bromine and iodine. Similar would be the reactions of bromine and iodine. That's about the cold dilute. Suppose if you wanted to have a hot concentrated NaOH, with chlorine, then you have this chlorine, NaOH, then you get Cl minus and ClO3 minus. Now what is happening here? It is 0 is giving you minus 1. 0 to minus 1. And the same 0 is now giving you plus 5. So it is 0 to plus 5. So this is what? Reduction. This is what is called oxidation. And this reaction, of course, will be called as disproportionation. You must understand this. So generally, what is the action of halogens on what? What is the action of halogens on bases? Then you must say that all halogens will be undergoing disproportionation with bases. Disproportionation with bases, which is like a redox reaction, and where the same element will be undergoing both oxidation and reduction. Not all halogens except what? Except what? Fluorine. So I wanted to compare chlorine reactions with chlorine side by side. You check out, one is disproportionation, the other is not a disproportionation. Watch carefully here. Watch carefully here. Suppose if I compare both these side by side, watch here. To avoid any confusion, what I'm doing is basically I'm giving you examples, disproportionation reactions. Examples of disproportionation reactions. Right, the best examples would be chlorine, bromine, and iodine with what? NaOH. They all undergo disproportionation except fluorine. Right? For example, what is the case of chlorine here? Chlorine plus NaOH. One of the reactions is it is Cl minus and ClO3 minus. right? Or Cl minus and ClO minus. You can understand. But if you look into fluorine here, with NaOH, you get OF2 and NaF and water. And this is not disproportionation, not disproportionation, not disproportionation. No, it is not disproportionation. Whereas this is what? Disproportionation. What's this? This is 0, it is minus 1. So it is basically 0 to minus 1. That is reduction. The same 0 is now becoming plus 1. So it is 0 to plus 1 oxidation. And this is an example of what? Redox, or I call this to be disproportionation. Whereas in this case it is 0 and this is this is minus 1. So it is 0 to what? Minus 1, that is reduction. The same 0 here is again minus 1, right? This is minus 1. Same 0. So 0 to minus 1, this both are reductions. This is reduction, this is reduction. So this is absolutely not a disproportionation. You must understand. That's absolutely not a disproportionation. So the sweeping statement is important to remember for the exam. What is the action of halogens? What is the action of halogens on bases like NaOH? This is the question. Then you say that all halogens will undergo disproportionation with caustic soda except fluorine, which will not undergo disproportionation or redox. Right? So same element undergoing both oxidation and reduction can be called as what? Disproportionation reaction, you must understand. Also remember, there is one question, and I'm telling you, I'm warning you, rather you put a star, note down this, bank on it, mug it off, understand, and whatever you do, in all the exams you will get this question for sure. Right? What is it? It is also disproportionation. But the way it is asked is different. Watch carefully here. I give another example. Please understand here. You remember there is something called allotropy, right? And there is something called allotropy. And basically allotropy is a function of nonmetals, right? Nonmetals, because allotropy is shown by nonmetals, not metals, right? So, in this, the question was like this. If you look into, if you actually look into this question, this is asked and very, very, very important for exam. Very, very important for exam. And this is under disproportionation. Right? Watch carefully here. If this is the case, then what is the question? How do you distinguish, or he has given like this, which of the following reagents shall distinguish, which of the following reagents shall distinguish red phosphorus from white phosphorus? White phosphorus. Which of the following reagents shall distinguish red phosphorus from white phosphorus? Remember that you have allotropic forms of phosphorus. When you have allotropic forms of phosphorus, one of the following is red, one of the other is what? White phosphorus. Now the question is asking is how do you distinguish this white from what? So understand that one of the questions which you can bank on, and I'm telling you, you will get this question in the exam. You will be getting it in the exam. And the way the question is asked is something like this. Remember, which of the following reagents shall distinguish red phosphorus from white phosphorus? Now, what is this red and white phosphorus is? Phosphorus is a non-metal, so you can have, several forms of phosphorus because allotropy is a function of what? Non-metallic nature, right? And I pick up, from the options, I picked up this. I picked up a base. Look into the way I think while answering the question. Look at the way I think while answering the question. It's all about phosphorus, right? So if it is all about phosphorus, phosphorus is a non-metal. Phosphorus is a non-metal. When phosphorus is a non-metal, then understand that it is non-metallic. Right? Non-metallic means it will have acidic nature. Acidic nature is a function of non-metallic nature. So clearly I understand that phosphorus is a non-metal and acidic. So it has only one duty to do. It has only one duty to do. React with what? Bases. So common sense is, out of all the options available, I would like to put my hands only on a base. Forget about the question. Phosphorus is a non-metal, so it is acidic, and acids are supposed to react with bases. So my answer from the 4 options would be, first pick out what? Pick out what? A base. Pick out what? A base. And one of the bases given is, of course, what? NaOH. So now, which of the following shall distinguish red phosphorus from white phosphorus? If you're saying, then I understand that red phosphorus plus NaOH, absolutely no reaction. In fact, it does not dissolve at all. It does not dissolve at all is a red phosphorus. On the other hand, if you take white phosphorus, which is having a tetraatomic, it is basically in a tetraatomic state. This is white phosphorus is not P, it is P4. It has, it is actually connected to 4 other phosphorus atoms, and that is how white phosphorus is. Since white phosphorus is basically acidic, we expect this white phosphorus, this is W, right, with NaOH, then you're supposed to get phosphine gas. You get that phosphine gas, and you're supposed to get NaH2PO2. NaH2PO2, sodium dihydrogen phosphite, hypophosphite rather. Sodium dihydrogen hypophosphite, right? It's a salt of hypophosphorus acid. So it's the same reaction if it is P4 red. If you take NaOH, then you get absolutely no reaction. No reaction meaning no dissolution. You must understand. So if you look into this, now why I'm discussing this here at this juncture, in this context, why I'm discussing this, remember when you have this, look into this reaction what you're writing. P4 plus NaOH, and this must be white because red doesn't. This is basically PH3 plus NaH2PO2. Look at this. This is a tetraatomic, this is an elemental state, so its oxidation state is 0. And in phosphine, it is -3. So it is 0 to -3 is basically reduction. Must understand. Similarly, the same phosphorus is now undergoing, look at this is +1. So the same phosphorus is now giving 0 to +1. So this is oxidation. So you have reduction, oxidation, and it is the same element which is undergoing both oxidation and reduction. So you must understand this is the best example of even disproportionation. You must understand this. This is an example of disproportionation. So if someone is asking you, give examples of disproportionation, then you can say all halogens with caustic soda will undergo disproportionation except fluorine. And also understand that phosphorus, to distinguish red phosphorus from what? White phosphorus. It is the white phosphorus which will dissolve in NaOH, giving you phosphine and sodium dihydrogen hypophosphite, the chemical name of that compound, in which the phosphorus is +1 and in phosphine it is -1. So 0 becoming +1 and the same 0 becoming -3 is an example of the same element undergoing both oxidation and reduction. So I consider this reaction to be what? Disproportionation reaction, you must understand. Right? So that is about disproportionation, that is about redox. But people might ask me, why is this red phosphorus not dissolving in what? Caustic soda. Remember that normally what happens is if the molecular weight of a substance is too large, it is giant, polymeric, In nature, normally polymers have molecular weights in crores and lakhs. Lakhs and crores. Right? So that's why most of the polymers are not soluble. Remember that if there is no solubility, then understand that it has a giant molecular weight. That means it has a giant molecular structure, polymeric structure. And this also has a giant polymeric structure with huge molecular weight. So thereby you must understand it's not soluble in water, whereas white phosphorus is tetraatomic. It's just tetraatomic. So I think it dissolves in water, giving you what phosphine. So it's basically the white phosphorus which will undergo disproportionation and not the red phosphorus. You must understand. You must understand, right? So that is about the redox reactions. That is about what? The disproportionation reactions. I think you are clear, right? Now let's go ahead and see some of, now what do you mean when we have so many things in our hand in stoichiometry? We have so many things in our hand in stoichiometry, then we wanted to know something else. When we know mole concept, we know concentration terms, we know percentages, we know molarities, normalities, redox reactions, disproportionations, oxidation numbers, we know so many things, then even we wanted to know this. Right? Now what is a stoichiometric equation? What is a stoichiometric equation? What is a stoichiometric equation? What is a good stoichiometric equation? Right? Then remember, a good stoichiometric equation will contain three things. Right? The first thing what is given is equation must be balanced. It must be what? Balanced, right? That is the first condition for a stoichiometric equation. It must be balanced. Then the second one, it should show the states of all reactants and products. It should show the states of all reactants and products in the balanced equation. Right? Whether it's a gas, solid, or whatever, you must be showing it. And the third one even should show heats liberated, or even sometimes even what? Absorbed. So you must say whether it is exothermic or endothermic. All these are the conditions for a good stoichiometric equation. Now, people might ask me, why are you worried about a good stoichiometric equation? Man, what is it you're supposed to do? What is it you wanted to do? That's the question, right? What is it I wanted to do with a good stoichiometric equation, right? You wanted a balanced equation, you wanted a products of reactions and products, and all this. Once you have a very good stoichiometric equation, then you can have problems. When all these are ready, then you can have problems, weight, relationship, because everything is there before me. I can have a weight-volume relationship. 3, I can have volume-volume relationship, and I can have even the concept-based problems and even the limiting reagent issues. Limiting reagent problems. You must understand, limiting reagent problems. So once you have, so for doing or for attempting all these problems, you must be in the equation must be right readily in your hand in this fashion. It must be balanced. It show the reactants and products, whether they are gases, such that, I can go in for either weight volume or volume. I need to know this. Right? So remember, then also it should show the heats liberated, whether it is exothermic or endothermic reactions. You must understand. Let us take one problem that is concept based, then we will take the remaining things, right? Let us take a concept based problem, right? Observe carefully here. Observe. Please observe. Concept based problems. concept-based problems in stoichiometry. Well, understand, look into the question first. I would like to write the question. And we have to identify that it is concept-based, right? Look into this. What is telling 1 gram of 1 gram mixture. 1 gram mixture. 1 gram mixture of sodium carbonate and calcium carbonate. 1 gram mixture of sodium carbonate and calcium carbonate. On heating, gave 224 milliliters of carbon dioxide at STP. At STP. Then he's asking, find percentage of sodium carbonate in the mixture, or even he's asking, find the percentage of calcium carbonate in the mixture. That's what he's asking. Look into the problem. He has mixed 2 salts, this and this, and the total weight is 1 gram. And he has heated this. Then you're supposed to get 224 milliliters of carbon dioxide at STP. Right? And then he's asking, what is the percentage of this and what is the percentage of this in the mixture? Well, I consider this to be, this problem is basically concept-based. So if someone is not knowing the concept behind it, you cannot do the problem. But one thing is sure, common sense. If someone is asking you, what is your percentage? Then how do you calculate percentage? Your marks by total marks into 100. That's percentage. If someone is asking, what is the percentage of mathematics? Then your marks by total marks into 100. Right? Similarly, suppose if he is asking, percentage of Na2CO3, then what you do is, let the weight of Na2CO3 be X. Let the weight of Na2CO3 be X. Then your weight by total weight into 100. This gives you percentage of Na2CO3. Your weight, that's X, by total weight is 1 into 100 gives percentage. Similarly, let the weight of CaCO3 now will be 1 minus X, because the total weight is what? Total weight is 1 gram. So if one is X, the other is 1 minus X. So if you want percentage of CaCO3, so it is 1 minus X by 1 into 100. That gives you percentage. So your marks by total marks into 100 must give you what? The percentages. You must understand that. Right? So he is asking the percentage of this in the mixture, percentage of this in the mixture, and this is concept based. Now what is the concept involved? Watch carefully here. Concept involved. Unless you know this, you cannot do the problem. You cannot do the problem. So what is the concept? Remember Na2CO3 is basically a first group carbonate. It is a first group carbonate. And remember, CaCO3 is a second group carbonate. And I'm writing a sweeping statement for you. And this statement you remember because this is also a question in exam. What is the statement I'm writing? Watch carefully here. This is a sweeping statement, mind you. All alkali metal carbonates all alkali metal carbonates, right? All alkali metal carbonates will not, and I am dancing here for a moment. It is will not will. All alkali metal carbonates, that is alkali metal carbonates, I am referring to what? The first group carbonates. All the first group metal carbonates, metal carbonates will not decompose at all on heating. No metal carbonate will decompose on heating. If you force them by putting high temperatures, then rather sublime. So let me write it properly. Look at the concept. Alkali metal carbonates won't decompose on heating. Rather sublime, except, there is an exception, lithium carbonate, which is not given in the problem. He is telling sodium carbonate. It's not like now lithium carbonate will decompose. What I'm telling is, if you actually see lithium carbonate and heat it, then you're supposed to get Li2O plus carbon dioxide. Whereas sodium carbonate will give you sodium carbonate on heating. This is a solid and this is a gas. Well, sodium carbonate giving sodium carbonate. It won't decompose. It won't give you carbon dioxide. It will not give you carbon dioxide. Similarly, potassium carbonate, rubidium carbonate and cesium carbonate, all these on heating will become no carbon dioxide. They won't. They will not. Except what? Lithium carbonate, you must understand. You might ask me why. Well, it's almost like, you're walking on the road, you see a big dig, right? You have a gutter, right? When you're walking on the road, you see a gutter. When you see a gutter, you say, oh, gutter, and you fall down. No, absolutely you don't. You take back, right? When you see the gutter. You take back when you see the gutter. So no alkali metal carbonate will decompose. And if you can ask me why, I'm giving you an example. You walk on the road, you see a gutter, then you see a gutter, oh gutter, and will you fall down? No, you're taken back, right? Similarly, if you say here, lithium carbonate will decompose because the size of lithium and the size of oxygen are same. There is a size compatibility. But if you take sodium, it will give you sodium oxide. Sodium is big, oxygen is smaller. The compatibility is not there. It's like going to the gutter in the RHS. And potassium is so big. So if it goes to RHS giving you K2O, potassium is so big, oxygen is small. So it will not go. It's almost like getting into a gutter. So what I mean to say, the subject point is, watch carefully here. Subject point is basically this. Alkali metal carbonates on heating, no carbon dioxide at all. Remember that. Whereas alkaline earth metals, right, that is the second group carbonates. Second group carbonates will give you carbon dioxide, yes. And this is no. That is the case. So now look into the problem. He says 1 gram mixture of this and this on heating gave carbon dioxide. That means this is the culprit and this is not. So what we will do is, the problem what we do is, total mixture weight is 1 gram, out of which let the CaCO3 be X. Then sodium carbonate will be 1 minus X because the total is 1. And remember, this gives what? Carbon dioxide. This won't give what? Carbon dioxide. This is so. I prefer writing the equation for CaCO3. So the CaCO3 is now giving CaO plus CO2. Wow, this is yes. This is yes. And he has given the volume of what? Carbon dioxide. So if you actually see, the truth is, if you see 1 molecular weight of this, it comes to 100 grams. This is molecular weight. This is giving you 1 mole. 1 mole of carbon dioxide will occupy 22,400 milliliters at STP. So if anyone anywhere in the world is heating 100 grams of calcium carbonate, you will get 22,400 milliliters of the gas at STP. But how much did you get? 224. And it is all given by calcium carbonate and it's not given by sodium carbonate. So if 100 is giving this much, 224 will give you how much? So that will be equal to 224 into 100. 224 into 100 by 22,400. This is what it is. Cancel it off. 100 cancels. Then you are supposed to get 1 gram. 1 gram. So the weight of the calcium carbonate is X. So how do you find percentage? So percentage of calcium carbonate is equal to weight of calcium carbonate divided by total weight into 100. So what is the weight of calcium carbonate? You got it? That is 1 gram. So what is the total weight? 1 into 100. So that is equal to 100%. So everything is what? Calcium carbonate. So percentage of Na2CO3 is absolutely 0. There is absolutely no sodium carbonate at all. You must understand this. Where do you go wrong is, if you don't know the concept, if you do not know the concept, what you will do is basically, if you do not know the concept, you will write even sodium carbonate equation giving you Na2CO3 giving rise to Na2O and CO2. Calcium carbonate gives CaO plus CO2. Both you are writing. But the fact is, on heating, he says on heating, right? On heating, no alkali metal will give you what? Carbon dioxide at all. Whereas the second group carbonates, yes, they give what? Carbon dioxide. It is not the first group. If you do not know this concept, it looks absolutely silly for you. Right? So, remember this concept again. Remember this concept again, which I would like to write it for you. Watch carefully. Please watch carefully. First group carbonates will not decompose at all on heating. Prefer to sublime. Like sodium carbonate, whatever might be the temperature, you become sodium carbonate gas. Similarly, potassium carbonate, rubidium carbonate, and cesium carbonate on heating will give you K2CO3 gas, Rb2CO3 gas, right, and CS2CO3 gas. On the other hand, I would like to say all second group carbonates, right, decompose on heating. Like you can have magnesium carbonate, you get MgO plus CO2, yes. CaCO3 giving rise to CaO plus CO2, yes, and etc., etc. But not the first group carbonates. That is the subject point you must be knowing, right?